Hey guys, it's Wanderson from MadLab here. Let's start creating the twister effects in Houdini. First, let's create a geometry node. Rename this node to twister. Twister effects. Let's dive inside this node. Create a line. Create a line with length 40. Resample this line by maximum length of 0.5. Okay, the amount of points is good. Create now a sweep node just to make this line with thickness like a tube. Change the surface shape to round tube. Radius of 4. And cap type to single polygon just to fill the ends. And change the columns to 32. Convert this to VDB. VDB from polygons. We need a density instead of surface. Let's check the resolution. Resolution is okay. And right now, we are gonna create a pop network to simulate some points here. Let's call it the twister particle scene. Let's change the life expectancy of these particles to 4. Life variance around the 1. Let's increase constant birth rate to around 25,000. Before the cache the simulation, let's create a file cache. Let's rename this to cache. Cache particles twister. Create a .NET import fields. Here we need the path of the twister particle scene. Twister particle scene, pop object. Copy this name here and paste here. Change the presets to particles and change the object to pop object. Connect this here. Okay, let's go inside the particle, the popnet, and add some operations here. First, let's add a pop force. We can delete this merge node. In pop force, let's make the amplitude around 5. Create a pop color. We don't need actually the color, we just needed the alpha. Disable the color, enable the alpha, and use the expression. Change it here to fade with age. And let's see the simulation. The simulation right now doesn't look like a twister. We need to make some adjustment, create a wrangle, a vex code wrangle, to make the particles spin around the y-axis. For this, create a pop wrangle, rename this to pop twist. Let's color this to purple. And create some script here. This is not just a simple script. We have here some matrix multiplication to make the points rotate around this axis here. Create a matrix, create a matrix. Matrix M equal ident. Before, let's create some variables here. Float, magnitude. This magnitude, you calculate the distance from the point, distance from each point until the zero in X and Z position, excluding the Y. Length of a vector P, X, 0 in Y, P, Z. This is the length of the vector excluding the Y position. Another variable here, float val amp equals fit magnitude 5 0 to 0.5 into this value amplitude will create a float number to accelerate each particles in regards the position from the center. For example, this particle from the center will spin much faster than these particles far from the center. Another variable here is angle. Float angle equals radians. Let's create a channel here. Angle. Times pole. Val amplitude by 2. Vector, up vector. This is the direction that the particles will spin in Y. Direction of this 0, 1, 0. And now we create a matrix, and after that we rotate the points. Rotate the matrix M by angle, define it here, and the up vector should be the direction. Now just rotate P, multiplicate P by M. Let's populate the parameters here, the values. Angle should be 5. And let's see what is happening with simulation in the top view. You can see here the particles from the center rotate much faster than the particles far from the center. This vex here just rotate these particles around the axis. Now we can cache the simulation. Instead of save just all these attributes we don't need, let's clean up. Attribute delete all the attributes Except the velocity, we keep ID and alpha. We have some group here. Let's delete this group too. Group delete. Any group. And cache the simulation. Let's create a checkpoint from the particles. Particle sync. Organize these nodes. Let's create a volume simulation from these particles. Actually, these particles will drive the velocity of the volumes. Let's create. First, we need to create some Vex node here. Rename this to Vex. Density and part P scale. This Vex node will create a density attribute that should be used in the volume simulation, and P scale from each point. When you convert this to VDB, we need some sizing from these points in the VDB volume. At density equals rand ID multiplied by alpha. This line creates a random value from 0 to 1 and multiply this by alpha. P scale equals parameter P scale multiplied by alpha. Let's populate the parameters here. P scale should be around 0.2. The first field in volume should be density, and then work in the velocity step later. Let's create some noise to deform these points' position. Vector should be P. Amplitude should be around 2. 2.2. Range values from 0 centered. Animation and element size around 9. To avoid the static movement from these particles, let's introduce some noise, some deformation. Okay. Create a trail node around 10 units, just to increase the amount of points per points. Instead of just 1 point per particle, we create like a trail to make the density more interesting. Now we rasterize the attributes, convert to VDB volume, the density. This should be our density emitter. Let's introduce some noise here, because this is too flat, too uniform. We create a noise fog, volume noise fog. Let's multiply 0 centered in range values and element size around 3.5. Animation and clipping the processing to avoid too high values in the density. That's it. This is the density field. Density emitter. And now we need to create a velocity emitter. Let's compute velocity here. Create a trail to recompute the velocity because we don't need the high velocity. We just need a part of this velocity. Compute velocity around f matched by attribute ID. Let's flat the velocity in y. To avoid, just to make the velocity going upwards, we need to flat first, because if you check here the velocity vectors, let's check the velocity here, you can see all the directions from the velocity. We don't need this downward velocity. We just want to create the upward velocity. For that, we just need to flat the velocity in y first. Create a point velocity later. Here initialization, we just keep incoming and add velocity around the 0.3, 0.4 to make the velocity going upwards always. 0.3. And rasterize these points to VDB. Let's increase the voxel size by 0.2 and p-scale to 2. Create a checkpoint here. Ref velocity field. And merge these two checkpoints. Before we create a simulation from this density and velocity, let's cache these two fields. Cache, twister, smoke emitter, and create another checkpoint here. Ref emitter. Let's simulate. Our cache was done. Now let's create a Pyro solver. Rename this to Pyro solver twister. Disable the processing of a cache of the solver. Connect here. Let's prepare our setup here before we creating testing for the simulation. Let's create a cache to Easter, smoke, create a Pyro bake volume to adjust the shader, and create a final checkpoint. Alt to Easter and color to black. Here in the Pyro solver, let's change some attributes here. First, we need to change the simulation to dense. Use OpenCL. Sometimes when you use the sparse, Houdini crash sometimes. Then I change this to dense and stop the crashing when I create the caches. In the bounds, let's change the bound size. limit maximum size around 25. The bound should be around the same size of the density. Let's see the density, or the velocity. Yes, this is around the size here. Around here. Okay. In the searching tab, we can disable the temperature, disable the flame, and adjust the velocity around 0.1. In the fields tab, we can increase the dissipation like 0.15, disable the flame. In the shape tab, we can disable the buoyancy. We don't need to do upward velocity because we already have the upward velocity, the velocity field here. We can create turbulence around 100. In the advanced tab, we don't need to change anything here. In the output tab, we just need the density field. We can disable the color, velocity, flame, temperature. We can convert it to VDB and use 16-bit float. Let's see the simulation. Let's create a cache. Now you can see some cool simulation here. In the Pyro Bake, let's increase the density, shadow density around 2, and the smoke density scale to 5. Let's go outside and create some skylight just for viewport visualization. Oh, cool. Let's create a flipbook and see the behavior of the simulation. That's the result of the simulation. It's cool. Here you can increase to 30 FPS to make it faster. Playback. At the beginning here, you can see some artifacts from the density meter. You can make the opacity of the beginning here. You can animate the opacity to remove these artifacts. We can do this right now. For that, you can create here, or you can animate density scale. Actually, you can animate density scale here. Around the frame 30. Let's create a keyframe here, 0. Left click, keyframe, and around 80. You can increase back to 5. Much better. You can scale the volume too, the spinning volume. Around in X and Z. 1.3. Just to make it more bigger, more strong. Let's create a flipbook again and see what's happening. That's the result from alpha and the scale in X and Z. Right now you can create a setup in Solaris to make the render. Let's start the rendering. We can go up there and create a loop network to make the look dev and shader. Rename this to look dev. Twister. Let's dip inside. Create a SOP import. Rename this to twister. Let's grab the reference from the volume twister here. Let's create a dome light. I pick up some AGR file here. Let's create an arrow light from one side, main light, and the fill light. That's the main light. Create another arrow light. Rename this to fill. Let's create a camera first in the camera. Look to camera, lock. Let's see a cool visualization in the viewport. Create a material library. Before adjusting the R lights and the lights, other lights, let's apply the shader. Material library. Create a Karma cloud material. Rename this to Karma Twister. Let's go inside. Increase the density around 10. We can change the shadow color around the bluish. You can zero out the extension. We don't need a scatter, and we don't need the anisotropic. Create a material assign to apply the shader to the VDB. Let's grab here the volume twister and the material. Create a Karma node. Rename the Karma to Karma Twister. Build. Change the resolution here. If you have a good graphics card, you can use XPO. Let's reduce the samples for previews. And adjust the R lights here. The first R light should be the fill. The main. Think around here. The fill should be the other side. Let's check if the R lights too small. Let's increase the size from both the R lights. Okay, 50. Too big. Left 20. And yeah, that's okay. Oh. Like 20 by 50. And move the other light, the fill, to the other side here. In the material, let's autofill materials to grab the Karma Twister and apply. We have already applied. Let's see the color, the render. Let's rotate the camera a little bit. Actually, let's separate more the lights. This light's almost the same position. Let's move the main light to the other side. Almost. Yes. And the camera should be around here. Let's see the render. Too flat. Let's decrease the R lights here. I think we need to decrease the DOM light. Activate the main light. We can increase the exposure from the main light. 5, good. Enable the R light fill and increase the exposure to around 3. 2. 7. Yes. Let's look the final result. That's the final result of our rendering. That's it, guys. That's the final look of the rendering. Thank you, guys. See you next video.